Now, a few things to note. This is going to be a long video again. If you want to try to scroll through, I will actually be mostly going through this script file instead of scrolling through that Google form, which just isn't very put together for a format like this. So you should be able to just track through and find out where I'm at. Cool. Let's get going. So the first example was, kind of a composite of multiple targets all put together, since it was meant to be the primary example. Just breaking this down though, what I've currently highlighted is actually the first extraction to run, one of 3. This by itself is the second extraction to run. And then finally, what I've highlighted all together here is the third extraction. Between the second and third extraction, there is a simple comparison being done, and that is all the functions in this line of code. So to the answer to how many extractions? 3. What dimensions are being subset in each extraction? This is going to be extracting from the column dimension. So that's going to be a 2D type extraction. This is also going to be extracting from the column dimension, a 2D type extraction. This, after the inside has resolved, it's actually created a single logical vector. And I'll talk you through that in a second. But at that point, there is only one argument, which means it's going to be acting as a one-dimensional extraction. But that's appropriate because after this extraction on the outside has happened, the data that wide extraction is pulling from is a one-dimensional object. And so it should be a one-dimensional extraction. So let's actually walk through this. So here we're going to use a numeric vector to extract from that second dimension. There it is. I just demonstrated that, yes, indeed, it is in fact a vector. Cool. So that means that anything we try to do to this needs to be treated as if it is a one-dimensional object, because it is a one-dimensional object after that first extraction. Okay, looking inside of here, this is going to look very similar, hardly able to distinguish it. The difference being that this is a different column, but the type of extraction and then the type of data inside of that column are the same. So we've isolated the contents of a single column. One of the things about R, a little bit tricky, is that if you use these square bracket tools and you get the contents of a single container, it will be a simpler object by default, as long as it's the contents of a single container. If you do have multiple columns, it doesn't simplify. Okay, so then we take that numeric vector, we compare it to the number 6 to generate a logical vector, so you can see some trues underneath my head. Then finally, we take that logic and we take what was a numeric vector on the outside and we do a one-dimensional extraction controlled by a logical vector. The final output is right there. Those small number of true values, mostly from near the end of the data set, where the third column of iris was greater than 6. So these are the values from the second column of iris where the third column of iris is greater than 6. And so that's really, what is happening all in one sentence. Let me just reverse that order. That output is a vector. There we go. Sorry for the sniffles. I'll get over it soon. Just some allergies this morning. All right, the next question asked about this line of code, a little bit simpler. Here we have an integer vector that's being created. This isn't the extraction yet. The extraction isn't just 1 or 2. It is only going to occur after the colon has operated. And so at that point, this is now a integer vector being sent to a single square brackets with a comma, which means it's going to be sent to the row section. It is going to extract all columns, but it is considering that two-dimensional structure of iris. Therefore, this is a two-dimensional extraction being controlled by an integer vector. because the output contains multiple columns, it remains a data frame. Finally, the returned data is the first 2 rows of iris, which is just how you would read that. That's how numbers work in extractions with single square brackets. This one is very similar. However, the only difference is that in this case, we narrow it down to a single column. And this is occurring all in one step. So in a single 2-dimensional extraction, we subset from 1 to 2 on the row dimension, and we subset the column dimension to just the first column. When you do that, R takes that opportunity because the contents of a single column is always a vector in a data frame. It simplifies that to a vector. And so contrary to 9, this one does have a vector as its output. If I'm trying to summarize it, I would say it's the first and second position within the first column. There you go. This next one, the $sign tool, is very simple. It opens up that container and extracts its content. The contents of sepal length is a numeric vector, and so that produces a numeric vector. Consequently, what I extract it with should be a 1-dimensional extraction, and that is what's happening. Note that there isn't a second argument here. Here is a second argument as comparison. Because of that, this works. So I get the first and second position of the sepal length column. There we go. I don't know why I try to reverse my body, the movement there. This next one is going to be the same extraction. So it's still going to produce a vector. It is being controlled by an integer in the row section. This was being controlled by an integer in a 1-dimensional positional extraction. But this is in the row extraction from a 2-dimensional. This is in the column argument from a 2-dimensional extraction. And so we end up getting the same data, 5.1 and 4.9, but using a different method. This time we're going to get some similar data, but the difference is that I've increased the number of columns. And so I said something a minute ago. I don't know if you're listening, but what will this do? Well, it turns out if you extract more than one column, R can't simplify it. Those are compartmentalized sections of memory. And so it won't simplify it to a single vector because it can't. Those might be different types of data. In fact, in this situation, they are different types of data. So it really couldn't put them together without somehow destroying the data or changing it in some way. Excuse me. So therefore, this will end up returning a data frame, not a vector, because it cannot simplify it. The rest is the same as that previous one. We have an integer vector here. We have a character vector here. Still a 2-dimensional extraction. The really main difference being that it's, right there. I guess I could just move myself, but it's kind of fun to wiggle out of the way. Okay, this next one, doing something a little bit fun, maybe not the most realistic. Not that I don't occasionally just do logic based on position. Okay, well, that time I really was covering up the truth. So there you go. If I run just that right side, we can see that it is logic. The way that it is being generated is I'm calculating the number of columns. You know what? I don't know why I didn't do this earlier. There we go. Much better. How long have I been doing this? 3 years? It's early. All right. So this is first calculating a vector of 1 through the number of columns of iris. And then I'm doing a comparison to pull out true values for anything greater than 3. I think in reality, I'd only be doing this method if I also had some other logic that I wanted to start doing, like combinations. So like, searching everything greater than a certain position and also contains the word sepal or something like that. This data frame is not that big, but in some of my really large data frames, like if I'm trying to isolate columns based on sample names, I may have hundreds of values. And so, manually picking out values like I've done here would be really tedious. And so I'll do stuff to generate logic that controls it in a little bit, more simple ways. Next week, when we talk about greps, which are going to allow us to do pattern matching, this will be a lot more understandable, and it would make more sense why you would generate logic in the column section a little bit better. This one, similar situation. I'm very frequently doing stuff like this on rows because this is a fairly understandable line of code. This is going to create true values for everything less than a certain position. So that is that vector right there. It's then being compared to the number 3, so we should see that this becomes true, true, and then the rest will be false. If we test that out, that is indeed what happens. At that point, I have a logical vector in the column section. I have a logical vector in the row section, and together they do a two-dimensional extraction, pulling out those rows and those columns. Because it is 2 columns, again, it ends up simplifying to a single data frame, not a vector. Had I simplified it to the contents of a single column, so I just increased that value so it's now only producing a single true in the column section, we do see that the data actually changed its type from a list type data frame to a factor type vector. And that is just a quirk of R. You just kind of have to memorize that if you are extracting more than one container at a time, it won't do any sort of simplification. But if you do extract a single vector, at least through most methods, single column, through most methods, it will simplify it to a vector. The exception to that is if you extract it as if it is a list vector. So using if you use a one-dimensional extraction on a data frame, it will not simplify it. Okay, this next one, this extraction happens first. This is a tool called double square bracket. It is completely analogous to the $ tool, which means it's going to get the contents of a single container. Really, the only difference between it and a $ is that you need quotation marks around the name of the column, or it can allow you to use the number. So like I could have replaced this with 5 and it would still work. And that's not true for a $. You can't use a number for a $. Okay, I'm going to pause this video for a second because I need to sneeze. Okay, I just sneezed like 10 times in a row. Fun. Hi. All right, let's do this. Where was I? Yeah. All right. So last we left off, which was no seconds time ago for you, was Iris had just been extracted from that 5th column based on its container's name. Now, the extraction did not produce a data frame. It produced a vector because that's what double square brackets does. Much like $, it gets the contents of the container, not the container itself. At that point, a second extraction takes place, this one being a one-dimensional extraction. Now, I will have students tell me, like, but Nolan, there's a comma in there. Well, that comma doesn't matter. That comma isn't seen by the square brackets. That comma is part of the C function. The C function combining values into a single object. So this was a length 1 numeric value, a length 1 numeric value, having been combined into a length 2 numeric value, but that is a single object. I said numeric value, I should have said numeric vector. Sorry. So using that single argument, we are going to extract those positions because that's how square bracket operates. So I'm going to extract the 1st and the 100th position from that species vector. That's it. When you run that all together, there it is. It's the 1st and the 100th position within the species column originally, but after that extraction, the species vector. All right, and the last kind of like just question of that type. More of just a fun little exercise and showing you a function called mod. First generating 1 through 50. I put that in parentheses just in case it mattered. I don't actually know if it mattered. I don't know where mod fits in order of operations. I don't use it often enough. I think I did test it out though, so I think it didn't need them. Once I've done that, and this is the interesting thing, we can see that 1 returned 1. Okay, so that is 1 divided by 20 has a remainder of 1. 19 divided by 20 has a remainder of 19, but 20 divided by 20 has a remainder of 0, and so that returns 0. 21 divided by 20 had a remainder of 1, and then this process repeats, and so we can see another 1 here, another 1 here, another 1 here, and that's important because I'm about to compare this vector on top of me to the number 1, which means I'm going to end up getting a true value every 20 values. Nifty little trick, right? Allow me to pull out different values based on the remainder after division. This right side, creating a vector of -1 through -3. That's an integer vector. This is a logical vector being used inside of a square brackets with 2 arguments. Consequently, 2-dimensional extraction of iris. I should have, after removing columns 1, 2, and 3, I should have 4 and 5 left, which means 2 columns will be remaining. So that's going to end up producing a data frame. And I believe I've now answered everything except for what is conceptually happening. Well, what is conceptually happening is I'm going to extract everything but column 1 through 3 across every 20 rows. That's it. Kind of a convoluted line of code. Not one I haven't had to do. I have actually, done some things like that before just to help parse some really big data. So I just can see little snippets all throughout, little things like that. And sometimes I know what columns I don't want, but I don't know how many columns there are in total. So I just remove the ones I don't want, which leaves me with the ones I might want. And yeah, nice little trick. All right, this next line of code is going to be doing an ampersand. So this is going to be extracting from the sepal length column. 2-dimensional extraction using a character vector results in a vector by itself. Then compare a numeric vector. Then compared to the number 5, that numeric vector becomes logic. There we go. Those are the positions in the iris object originally where the sepal length is less than 5. And, that's how we read ampersand, and where the sepal width is less than or equal to 2.5. I'm then using that combined logic. So this was 1 over here, then this was another. Please note that the trues and false change. So what was false was now sometimes true, and vice versa. But once I combine them, it's only true wherever both situations were met. And so if I look at the output, I can see that that's actually only 3 different positions. The sepal length is less than 5, true, and the sepal width is less than or equal to 2.5, also true, and therefore they got extracted. The joining was the key step here. The ampersand means that both situations have to be true. Okay, this next one is basically the same. Wait, no, is it literally the same? Yes, it is literally the same concept, except the extraction is going to also reduce to just petal width. So in this situation, I have subset based on sepal length being less than 5 and sepal width being less than or equal to 2.5. And then I'm using that as a filter to isolate the values that correspond to that, but for just the petal width. So 0.3, 1, and 1.7. 0.3, 1, and 1.7. Nifty, right? That means I could use this in some math. This is data frame, and I'd have to extract from it subsequently to use it in math. So the different shapes matter for your downstream analyses. Sorry, very sniffly today. I'm gonna pause again. You'll be happy to know. No sneezes, just sniffles. All right, moving on. Next question. The next question is iris $ sepal length less than 5. That's going to produce a vector of numbers, just like before. $sepal width 2.5 less than or equal to 2.5 again, but this time I'm combining them with an or. So it's with if either one is true, we're going to extract that position. So when I combine those, I can see that it has a lot of true values, and that's because it has however many where at least one of those tests did return true. Much like this last one, I'm extracting from petal length, but this time, instead of using a two-dimensional extraction, I'm going to extract from that container first using the $, which is I don't know how to think about it. It's technically the name of the vector, which the vector has an underlying one-dimensional structure, so kind of a one-dimensional. I haven't really asked you to categorize $, if you haven't noticed. But anyways, $, is going to do its thing. It's going to open up that container. And then from that resulting vector, I'm going to be using the single square bracket tool in one-dimensional mode to extract those true positions. So in summary, where the petal width will be extracted where the sepal length is less than 5 or the sepal width is less than or equal to 2.5. That would have been sufficient. A lot of different ways to say that, though. All right, this next one is going to generate some data. So I'm going to visualize that data. Look at that. We got 2 columns. This column's got some missing information in it. Probably going to be a question about how to deal with missing information, I'm imagining. This is me visualizing it. This is me showing how logic will work on a object containing missing values. It turns out it will, one second, let me raise that up. It will contain missing values wherever the original data contained missing values. If I then, however, take that same logic, so please note that this is the logic I just printed out, but now I've wrapped which around it. I no longer have missing information. I only have the positions which are true, 1, 2, and 4. This is actually quite nice because if I was trying to extract from that data frame with that missing data, it actually creates rows of missing data. And please note, it's not that it extracted the row with missing data. It extracted rows of missing data. A subtle difference, but one that can really impact downstream analyses. So handle your missing data better than this. This is just introducing more missing information and maybe even destroying something that I didn't intend to destroy. Anyways, the which, on the other hand, is going to successfully omit those missing values. So like that was my choice. That's what I could do. If instead I wanted to pull out the values which were either this or missing, I could use the or symbol, analyze the second column using that or symbol. And with that, I do end up getting true, 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 false, false. So that is actually an improvement. I think that was not true in previous versions of R, but now if you do this, it does produce a usable vector for then extracting anything with either a value less than 10 or missing information in column 2. So if that was what you wanted to do, that would also work. Not what I asked, but that would technically work. All right. Next up. These were just asking you to predict what was going to happen. This is going to be a little bit more simple, a little bit more similar to how I might ask you questions about comparisons on the exam. Although I'll be honest, there's a lot of iris-based questions on the exam as well. I don't ask you for a lot of these classifications, though. Some of the classifications is a little bit muddy, turns out. Anyways, so here 1 through 5 being set equal to 2. Well, that's going to be false, true, false, false, false. False, true, false, 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 because only the value 2 in 1 through 5 was equal to 2. Not equal to 2 is going to be the opposite. I also could have just taken all of this and literally done the opposite. It works. Exclamation point is going to be not. It is a negation of what was ever there. When combined with equals, it becomes not equals, but here's an example of just that one. Okay, in this situation, we are using the single square brackets tool on 1 through 5. Did get a surprising number of questions about this one in class. I'm not sure why. I think it's just you get a little bit used to seeing the square bracket in that previous context, but square bracket just works on anything it has instructions on how to parse, and that's most objects in R, which is why I'm bothering to teach you about it. So in this situation, 1 through 5 is an object. It's going to be an integer vector. I'm then extracting that second position, so that's the number 2. So that resolves to integer 2, actually. And then it is being asked, is it not equal to 2? That is a false statement. So it is equal to 2, so not equal to 2 is false. You have to kind of like flip your head around a little bit. Usually that's I find the best way to ask that is that a true statement? If it's a true statement, then you say true. If it's a non-true statement, you say false. So in this situation, 2 not equal to 2 is a untrue statement, and so it is false. This situation is just going to be true, true, false, 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 false. I should probably take that one out. That one's not really carrying much weight, is it? This next one, we're going to generate an integer vector on the outside. We're going to generate a same integer vector on the inside. But then we are going to compare it to the number 3. So true, true, false, false, false. That is going to use logic in a one-dimensional extraction, producing 1 and 2. Weird sounds. Sorry about that. Next one is really why I asked that last question, just to draw your attention to. Here, I have taken the exact same code. I've then negated it, which means false, false, true, true, true. So I get the opposite values out, 3, 4, and 5. Finally, this one is just demonstrating. I could just manually combine values. I don't really recommend it, but I can do it. As long as they're the same length, it should operate pretty predictably. When they are not the same length, that is when you get some weird nonsense. Try to make them the same length. I get the 3. I get the true values. Okay, now I believe this is getting 2 more questions. Okay, column options. This is going to be a vector just containing these different values. On the left side of my percent and percent, I'm calling the column names. I'm then comparing each of these values, because this is how percent and percent works. Compare each of the values on the left in the list of options to the right. Vector of options. It can actually be a lot of different types of data on the right. But basically, if this value is anywhere in this object of options, it is going to return true. And so please predict in your head, will that be length 5 or length 3? 5, 4, 3, 2, 1. It is length 5 because I said each value here is going to return true or false. Is it anywhere inside this object? So I get true, true, false, false, false. Made up column doesn't end up doing anything because it's not a match to anything. And that's the direction of the order. If I had reversed that, it would matter. But if I had reversed that, it also wouldn't be the right shape for extracting from the column dimension of iris. That should definitely be an impactful statement, because I think that's where a lot of students get confused, is whenever they're doing extractions, you're just trying to learn this right here. I get it. But you do have to think about the whole context. The reason why this works is because it was based on column names. So it is the right shape. It's length 5, so is that column dimension, because it was based on the original object. So that's why this works. This is a length 5 logical vector extracting the 2 columns from iris that had been determined to be true based on that percent and percent. So sepal length and sepal width. That's it. I want you to think real quick, what is going to happen if I flip the order here, I should have done this, actually. That would have been fun. If I flip the order, what is this going to do? 3, 2, 1. Okay, so these are still the options. The thing that's going to control the order is the column name object, because it is being tested in order. So it doesn't matter what order the options are. These are just the options. It's just this is what determines whether or not it returns true or false. But this is what determines what value is being tested in any given logic. And so this still returns the exact same data it did last time, because the order was dependent upon the column's name object, which had a particular order to start with. I know, I'm so sneaky. Okay, last question. DF1. DF1 looks like this. Letters A through Z, numbers 1 through 26. Not too bad. I'm then doing a series of logic and trying to, good job, dog. I'm doing a series of logic and trying, that was my dog barking, by the way. I don't know if that came through. I didn't just go, good job, dog, out of nowhere. Fun statement. So here we are calculating which of the values in that column are greater than 10. So we can see that the value is greater than 10 or greater than 10. And then returning or the values are less than 20. And so it's going to help to see these side by side. An or is going to return true if either one is true. And so false or true, false or true, that pattern continues, and then you get down here and it's true or true and true or true. Okay. And once I get past 20, it's false and true. In other words, I've actually selected in both directions and they've overlapped completely. This has selected all of the original data because any number is either less than 20 or greater than 10. That is all numbers, all real numbers that is true for, out into infinity on both sides. Nifty, right? This next one, it says less than 10. Okay, so that's going down, or greater than 20. So if I'm thinking about how they overlap, this is kind of the opposite. This is, I can't bend my elbows that way. It's going this way. So if this is 10 and this is 20, 10, 20, I'm pointing outwards with nothing in the middle. So this is like an exclusion of everything in between them. So this would get just those values outside. So 1 through 9, then 21 through 26. The and is a little bit easier to understand, I think. Greater than 10 and less than 20, so that's going to be 11 through 19. There's your logic. See 11 through 19. Let's scroll that up real quick. And then finally, less than 10 and greater than 20. That one's impossible. That's zero. There are no numbers that are simultaneously less than 10 and greater than 20. And so this returns all falses and therefore an empty data frame. So in summary, every single value, not because of the thing you need to memorize, but because of a thing you should be able to reason out. All values that are outside of 10 or greater than, or sorry, lower than 10 or greater than 20, again, not memorized, understood from looking at this logic and really just sitting there and playing with, maybe even just sketching it out on a number line until you figure it out. This is going to be just in between. And finally, less than or greater than the larger number is completely exclusionary of all numbers. And so that returns nothing. Okay. That actually reached the end. Not as long as I thought it'd be. So I hope that helped. Please, send me some messages if any of that's unclear or if I made a mistake. I don't think I did, but nothing major at least. Anyways, y'all have a good day and thank you for your attention. Bye-bye.